Section 1.2 involves us using the definitions of all the trigonometric functions. We're going to add a lot of definitions today that allow us to find relationships between the 6 trig functions. Okay, you already know these reciprocal identities because we could see them from the definitions of the trig functions. But this is going to be very important for us, our reciprocal identities. Reciprocal means flipping the fractions. So just like we noticed probably last class that sine and cosecant were like flip fractions of each other, they are called reciprocals of each other. So it might be helpful to do like this business where sine and cosecant are a pair, cosine and secant are a pair, and tangent and cotangent are a pair. They are reciprocals of each other, so just like last time, their definitions are just reciprocals of each other. Y over R or R over Y, that's sine and cosecant, and on and on. Caution, make sure not to use the inverse trigonometric function keys on your calculator to find reciprocal function values. For example, the inverse of cosecant is not the same as the reciprocal of cosecant. So there's a button on your calculator above sine that says sine to the -1. Everybody see that? That is not what we're doing right now. That is not a reciprocal function. That's an inverse function. Those are different. Instead, when you're typing things in your calculator, you will literally write, instead of cosecant, 1 divided by sine, or 1 divided by cosine, or 1 divided by tangent. Don't use the sine, cosine, and tangent to the -1. Those are different. It's a different function. We'll learn about it later. But sometimes we don't even have to work that hard and use our calculator. Using the reciprocal identities, if we are asked to find cosecant and we know secant, here's the things I know. By definition, I know that secant of theta is always equal to 1 over the cosine of theta, which means that cosine of theta is equal to 1 over the secant of theta. So if secant of theta is 5/3, that means that the cosine of theta is 3/5. The end. I literally just used the reciprocal of that fraction since these two functions are reciprocals of each other. That's the fact, and that's how you use it. We're finding cosine of theta, given its reciprocal, just flip the fraction over. Okay, same thing, sine given cosecant. Since sine and cosecant are reciprocals of each other, all we have to do is flip that number over. But this one gets a little complicated because it's not simplified. If we flip this over, that becomes -2 over square root 12. A couple things need to happen here. First of all, are you allowed to put square root 12 in the denominator? No, so we're going to have to rationalize the denominator. But also, square root 12 is not even in simplified form. So if we take the number 12 and break it into a tree, isn't that 2 times 6, and 6 is 2 times 3? So I have a pair of 2's and a leftover 3, which means that this number is actually negative. I'm going to put the negative on top just to make it easier to write. Over 2 square root of 3. Now let's rationalize the denominator. Meaning I move the square root 3 to the top and I multiply the bottom. So we would have just left the 3 in the bottom from last class, but if there's a 2 already there, you're going to multiply them. Make 6. Ooh, but that fraction can reduce. Look at all this math we're doing. This ends up being negative square root 3 over 3. Huzzah. All we're doing is flipping that number over. Occasionally, there's a little bit of arithmetic to take care of afterwards. So example A just had us flip the number. Example B had us flip the number and reduce and simplify and rationalize the denominator. Oh boy. Easy peasy? Great. Now that we have the reciprocal values, the reciprocal function, what we can do is focus on the signs and the ranges of these function values. Notice that I'm not talking about the function sign, S-I-N-E. I'm talking about the signs, S-I-G-N, like is it positive or is it negative? Okay. Now, there is a pattern to all of this. If you're looking at an entire coordinate plane, in quadrant 1, all of the functions are positive. So we're going to put a giant A right there. You kind of can't see it because I'm writing in yellow highlighter. In the second quadrant, it says sine and cosecant are positive. So we're going to put an S right there for sine. The idea that cosecant is also positive there just follows since sine and cosecant are inverses of each other. In the third quadrant, it says tangent and cotangent are positive, so we're going to put a T right there. In the fourth quadrant, it says cosine and secant are positive, which are the reciprocals of cosine. So we have ASTC. If you took my class last year, do you remember the acronym I used? I mean, yeah, but do you remember the like words? All-star trig class. Boom, this is an all-star trig class. Look at you guys. Boom, boom, all stars here. All-star trig class. If you follow that in order of the quadrants, it lets you know which trig functions are positive. All of them are positive, sine and cosecant, tangent, cotangent, and then cosine and secant are positive in those quadrants. So part of the goal of this game that we're playing here is deciding the positivity or the signs, S-I-G-Ns, of the different trig functions per a particular angle. So all we need to do is figure out which quadrant the angle lies in, and we can tell the positivity, positive or negative, of each trig function. So let's say we're looking at 87 degrees. If you're looking at 87 degrees and you're drawing a quick little sketch of that, did we quite make it to 90 degrees? No, it's like a little bit less than 90 degrees, yes? This would be your theta 87 degrees. What quadrant are we in? Quadrant 1. Which trig functions are positive in quadrant 1? All of them. So we would write down sine is positive. I don't like the way I wrote that. Give it some space. Sine is positive. Cosine is positive. Tangent is positive. Cosecant is positive. Secant is positive. And cotangent is positive. Because all of them are positive. Check, done, too easy. Where is 300 degrees, though? Fourth quadrant. So remember the quadrants are 0, this is 90 degrees. Hello, Miss Quigley. 180 degrees, 270 degrees, and then 360 degrees. So 300 is somewhere in between 270 and 360. So my angle looks something like that. We're in quadrant 4. By the way, you list the quadrants in Roman numerals. So quadrant 4 is Q and then IV. That's 4 in Roman numerals. Which trig functions are positive in quadrant 4? Cosine and secant in quadrant 4. So that means everything else, like sine, is going to be negative. Cosine is the one that's positive. Tangent, positive or negative? Negative. Cosecant, positive or negative? Secant, positive or negative? And then cotangent, positive or negative? So our goal is to figure out which quadrant the angle lies in so that we can always double check later when these problems get bigger that we have used the correct sign, S-I-G-N, for the 6 trig functions. Okay, what about negative 200? What does that angle look like? First of all, does it go clockwise or counterclockwise? Clockwise, because that's the negative direction for angles. If I'm going clockwise, this is 0 degrees, this is negative 90 degrees, this is negative 180 degrees, this is negative 270 degrees. What quadrant would negative 200 be? Quadrant 2, because it's somewhere between negative 180 and negative 270. This would be your angle theta. So we are in quadrant 2. In quadrant 2, which trig functions are positive? Sine and cosecant. The rest of them are negative. So we would say sine, positive. Cosine, negative. Tangent, negative. Cosecant, positive. Secant, negative. And cotangent, negative. Make sense? So there's always a nice little double check for you if you know what quadrant your angle lies in, which you always should make sure you know, of which trig function should be what sign. Because eventually in this lesson, I'm going to ask you to find the value of all trig functions outside of quadrant 1. And so you're going to have to do positive and negatives. And making sure that you're in the correct quadrant and have the correct signs, S-I-G-N. Another thing you might see is the information given to you about the possible quadrants that an angle could be in with inequalities. This first inequality right here says that the sine of theta is bigger than 0. That means that sine is positive. And that tangent of theta is less than 0, which means tangent has to be negative. So we need to figure out which quadrant has a positive sine value and a negative tangent value. So we write down our all-star trig class letters. We're going to circle 2 sets of letters, and where they overlap, that's the quadrant you're in. So if sine is positive, what are the 2 quadrants where sine is positive? 1 and 2, A and S. It can be in quadrant 1 or in quadrant 2. The second option, or second value we know, is that tangent has to be negative. In which 2 quadrants is tangent negative? Second quadrant, where else? Second and fourth. Because the A and the T are where that is positive. So where is the overlap in my circles? S, which means that this angle must be in quadrant 2. Yeah. Say again? Yeah, it wants you to identify the quadrant. Yeah. It says identify the quadrant. Identify the quadrant. Can we try another? I don't think we have a choice, do we? You don't. For B, cosine is less than 0, which means cosine needs to be some negative value, and secant needs to be some negative value. Ooh, secant. Secant is the reciprocal of which function? Cosine. So here's our options here. Our overlap might be a little bit different for a question like this. If cosine is negative, which 2 quadrants is cosine negative?
2.
And? 3. Cool. Where is secant negative?
2 and 3.
2 and 3. So we only have enough information to narrow it down to 2 options here. We had an overlap in quadrant 2 or quadrant 3. So there is a possibility that you don't have enough information to narrow it down to 1, in which case you answer with both.
Okay.
But 90% of the time you're going to be given information to narrow it down to 1 quadrant. We'll pause there before lunch because we're like 20 seconds from going to lunch. But when we come back, we'll talk about the ranges of these functions. We can also discuss the ranges of the trig functions. So this is like domain and range. Yes? Domain is the x value, so range is the y value. So that's what we're talking about. We're talking about the possible outputs or y's that you're allowed to have for each trig function. Remember, this means these are the numbers that the function is equal to. So a sine and cosine function can only be equal to numbers between -1 and 1. They have a range that is bounded on the bottom and on the top by the numbers -1 and 1. You could only have trig values equal to numbers in between them. That's the range. Since cosecant and secant are reciprocals of those functions, the cosecant and secant range is like literally everything except for -1 and 1. So cosecant could be equal to a number like -10, but sine could not be equal to a number like -10, because -10 is outside of the range of sine, which means, bless you, it's inside of the range for cosecant. They are reciprocals. Tangent and cotangent, though they are reciprocals, have a similar or have the same range. And their range goes from -infinity to infinity, which means tangent and cotangent could be equal to any of the values on the number line from -infinity to infinity. Notice I'm not talking about the numbers you plug in. I'm talking about the numbers that you get out, the things that it is equal to. So we need to first just determine if each of these statements is possible or impossible based on the ranges of these functions. So can sine of theta be equal to 2.5? Why not? Yeah, sine can only be equal to numbers between -1 and 1. Is the number 2.5 in between the numbers -1 and 1? No, which means this is impossible. 2.5 is outside of the range of the sine function. Can tangent of theta be equal to 110.47? Yes, because what is the range of tangent? Negative infinity to infinity, all real numbers. It can be equal to whatever we want. This one is possible. Can secant be equal to 0.6?
Yes.
Let's think about the number 0.6. If we were looking at a number line, the range of secant is everything on the outsides of -1 and 1. So it's like here and here. Where is the number 0.6? In the middle-ish. So is 0.6 inside the range of secant? No, because the range of secant is from negative infinity to -1, and then from 1 to infinity. The number -6 is not in that range, so this one is also impossible. Again, we are talking about the numbers we're getting out of the function, not the numbers we're putting into it. You can put whatever angle you want inside these functions and get a value. For the most part, sometimes it's undefined. I digress. Okay. Example number 5 is kind of like the meat and potatoes of what today wants you to do. It combines what we did last time with a little bit more information. We're still going to find all 6 trig values, but this time instead of giving you a coordinate point, they've given you a ratio and information about the quadrant in which this angle is. It says, suppose that angle theta is in quadrant 1 and sine of theta is equal to 2/3. We're going to find the values of the 5 remaining trig functions. All right, let's first start with the information we're given. If we know sine of theta is equal to 2/3, out of the values of x, y, and r, based on the definition of sine, which 2 of those 3 letters do we know?
Both X and Y. Y and R.
We know y and r. What's the value of y? What's the value of r? This is why knowing our definitions of these trig functions is very helpful. Sine is always y over r. Which means, like we did last class, what can we do to solve for x? A squared plus b squared equal to c squared. Pythagorean theorem, solve for one of the side lengths, which means we're going to take the radius squared, which is 3 squared, and we're going to subtract the other side length squared. Did we do this in this class? I'm teaching the same concept in 3 different classes, and I can't remember what I've done in what class. So if I ever do something and you're like, you didn't do that, tell me, because 3 of my classes are overlapping right now. Which is going to be 9 minus 4. What's 9 minus 4? 5. So we have the square root of 5. We're leaving it as square root of 5 because we can't take the square root of 5 unless you use a decimal rounded version. Okay, cool. We're almost there. However, it tells me that this angle is in quadrant 2. Based on all-star trig class, what are the only trig functions that are going to be positive in my list of the 6 trig functions? Sine and cosecant. So we have to remember now that since we're in quadrant 2, 4 of the 6 trig functions are going to be negative. So if we start to list them, we have sine of theta is 2/3. We were given that one. Cosine of theta would be square root of 5 over 3. And tangent of theta would be 2 over square root 5, but then you have to change that to what? 2 radical 5 over 5, yes. Once we have the original 3, we can use their reciprocals. Just flip that number over. Oh, wait, I messed up. What did I do wrong?
Oh, you need to put the negative.
I need to put the negatives. Which 2 of these are negative?
Cosine and tangent.
Cosine and tangent, my bad. So we remember that those have to be negative. See, this is why we always check those quadrants. I totally did that on purpose.
Yep.
Cosecant of theta should be equal to 3 over 2. Secant of theta should be equal to negative 3 over square root 5. Uh-oh. Just kidding. Negative 3 square root 5 over 5. And then cotangent of theta should be equal to square root of 5 over negative 2, which is fine. We can leave it like that.
Okay.
Comments, questions, concerns. This is kind of like the extension from last class to this class, thinking about then the ranges and the positivity signs, SIGS. GN, of these different trig functions in different values. Also, if you cared, here's the extension again. In quadrant 2, your coordinate points in quadrant 2 are always what comma what?
Sign negative positive.
Negative positive. Like if you were going to plot a coordinate point over here, it would always be some negative number, some positive number, yes? Which means that the x value has to be negative and the y value has to be positive. Every one of my trig values that used square root 5 are the ones that are negative. Because we're in quadrant 2. This is how all of it fits together. Yes?
Okay, wait, so I'm confused.
What?
Right, so when you put a negative in front of the square root, isn't that just I?
Oh, that's negative inside the square root. There's a negative inside the square root. You do have that become an imaginary number. If we're plotting coordinates, let me make sure I'm not lying. When we're plotting coordinates, since they're locations, we shouldn't get a negative number underneath your square root. I'm 97% confident by the scope of this course that's true. I don't think I lied to you. Okay. Can we go on to 2 more types of identities we're going to need to know? If you took AP Pre-Cal last year, you already know these identities, or I made you know them and you probably forgot them over the summer. But here are the other identities we're going to need to know. The first 3 are called the Pythagorean identities. These look familiar, AP Pre-Cal friends? Great. The Pythagorean identities are derived from Pythagorean theorem with the concepts of x, y, and r. In AP Pre-Cal, I made you derive them. In this class, we're just going to use them. The most important one, the one you're going to use the most often, is sine squared plus cosine squared equal to 1. This comes from Pythagorean theorem, substituting in our values for sine and cosine in x, y, and r. Great. The other 2 are still important, so don't just count them out. This one involves tangent and secant, and the last one involves cotangent and cosecant. These would probably be things I'd put on the front page of my notes for use on my test. I will have them on our vocabulary quizzes, but for our actual tests, for the chapter test, you can put these on your formula chart that you make for yourself. Just saying. The other identities we have on this page are the quotient identities. Quotient means dividing. These quotient identities, I think we've already seen. Again, that might have been in a different class. But tangent can be written as sine over cosine, which honestly is going to allow me to have a better relationship between the sides and the radius of these triangles created on my unit circle or on a coordinate grid. So we can use these identities instead of the steps we did on the page before this to solve questions very similar to what we did first. Meaning, if what we just do, or what we're about to do in example 6 and 7, are very confusing to you, you can go back to the steps we did in example 5. They should still work. We're going to try something new here to give us some cool new ways to solve problems. This first question said that we need to find just sine and tangent, not all 6, given that cosine of theta is equal to negative square root 3 over 4, and that sine of theta is bigger than 0. First things first, what quadrant are we in if we have a cosine that's some negative value and sine that's a positive value? Let's do this piece by piece. Where is cosine negative? And I'm getting that from this right here. What? Cosine is a negative number. Quadrant 2 and 3 are where cosine is negative. Which 2 quadrants is sine positive? 1 and 2. So which quadrant is this problem, this angle, this theta going to be in? Quadrant 2. Okay, so we are always going to check and make sure that sine will be positive and tangent will be negative because we know we're in quadrant 2. Instead of telling me like we would have on the other side that this is the x value and this is the r value, which again you can totally do. You can also use the identities on this page to find a relationship between these values. Since we know cosine and we want to know sine, we can use the Pythagorean identity sine squared of theta plus cosine squared of theta equal to 1. Notice, by the way, if you've never seen this Pythagorean identity before, the squared goes right after the letters, not after the theta. If you put it after the theta, you're squaring the angle instead of squaring the function. So that's a notation problem. Okay, we don't know sine squared of theta, but we do know cosine of theta. Cosine of theta is this negative square root 3 over 4. So if I square that, it's going to be equal to 1. How many variables and functions do I have left once I've substituted that in? 1. I just have sine. I just have theta. I can solve. Yay. What is negative square root 3 over 4 squared?
I'm gonna find that out.
Oh, we can do this in our head. What is the square root squared?
Oh, it's just the regular number.
Just like cancels out the regular number. What's a negative times a negative?
Positive.
What's 4 times 4?
It's 16.
So this is actually just 3 over 16. Oh, math in our head. Okay, yeah, but then we have to do some math with some fractions. I need to subtract that 3 over 16 to the other side. Let's rewrite the number 1 with a denominator of 16. Which means I'm going to write this as 16 over 16. Because isn't 16 over 16 the same thing as 1? Okay, I just want to have it have the same denominator as my number I care about. So that I can subtract 3 over 16 to the other side, and I'm going to get 13 over 16. Okay, we're almost there. We want sine of theta. Remember, that was the question. Find sine of theta. But right now I have sine squared of theta. How do you get rid of a square? Square root. So sine of theta is going to be equal to the plus or minus square root of 13 over 16. There is a rule with fractions underneath square roots that you can split it. Square root on top, square root on bottom. Can you take the square root of 13?
No.
Can you break the number 13 down in any way? No, it's prime. So we're going to leave that as square root 13 in the top. But what's the square root of 16?
4.
4. Okay, question. I left the plus or minus at the very beginning.
Yeah.
But since we know we're in quadrant 2, is sine of theta going to be positive or negative?
Positive.
Positive. So I can confidently answer that sine of theta would be square root 13 over 4. If it happened to be a different quadrant, you'd have to use the minus sign. Yes?
How did you go from 3 to 13?
16 minus 3. Because I subtracted this fraction to the other side. Canceled it out over here. 16 minus 3 is 13. That's why I changed the number 1 to 16 over 16, so that they're the same denominator. We're halfway there because we did the first part. We found the sine of theta.
Oh my God.
What else do we need to find?
Tangent.
Tangent. Good thing that there's a relationship between tangent, cosine, and sine. Because we now know the value of cosine, we know the value of sine. What's the relationship between tangent and sine and cosine? Look right above this, the box right above. It's sine of over cosine. So I can substitute the values of sine, which is square root 13 over 4, and cosine, which is negative square root 3 over 4. So now, what we're going to want to do, is that better? Okay. How do we divide fractions?
That's a great question.
Keep, change, flip. So we keep the top, change the divide to a multiply, flip the bottom. What do you notice? Yeah, we have a radical 3 in the bottom. We'll have to take care of that. I notice this. Cancel out the 4s. I end up with square root of 13 over negative square root 3. We're almost there. Yeah. Can we leave square root 3 in the bottom?
No.
So we move it to the top. There's already a radical in the top. What do we do with those two numbers underneath the radical if they're both radical numbers? Multiply them, which means we're going to have square root 39 over negative 3. Ah, deep breath. That's tangent of theta.
Oh, thank God.
We're done with this one.
And it's only 140. It's only 134.
Well, guys, we have example 7. Do y'all want to try example 7 by yourself?
No.
Oh, okay. Great. Golly.
I don't know. I actually thought of it.
Was trying to give y'all props. Okay.
No.
Interesting. Okay, for this one, it's asking me to find sine and cosine, and I'm given tangent. based on the values up above, let's go first for the Pythagorean identities. Is there any Pythagorean identity that puts sine, cosine, or sine and tangent, or cosine and tangent together? No. Tangent, though, is in that middle one. What does tangent go with? Secant. Secant is the reciprocal of what function? Oh, so technically we do have a relationship between tangent and cosine. It's just the reciprocal. So we're going to use that middle trig function, trig identity, to help us out. Before we do this, let's make sure we've read the whole question. This angle is in quadrant 3. So if we already know it's in quadrant 3, which functions are going to be positive? Tangent. So sine and cosine will both be what? Negative. Okay, because we know it's in quadrant 3. Great. Fun fact for us to know. So what we're going to do is we're going to write down the middle Pythagorean identity. Tangent squared of theta plus 1 is equal to the secant squared of theta. Fabulous. Let's plug in what we know.
Okay.
What do we know?
Tangent.
Tangent. So this is 4/3 squared plus 1 should be equal to secant squared of theta. 4/3 squared. What is 4/3 squared?
16/9.
16/9. Very good. If I want to add the number 1 to it, how should I rewrite the number 1 to make that easier on myself? 9/9. Because 9/9 is 1, yes? We're making our lives easier. 16 plus 9, that's 25/9. Should be equal to the secant squared of theta. How do you get secant by itself? Square root. What's the square root of 25?
5.
What's the square root of 9? 3. So if secant squared of theta is 25/9, secant of theta is the square root of both numbers. Because just like above, square root of a fraction is square root of top over square root of bottom. Ooh, but that's secant. Do I care?
No.
What is secant the reciprocal of, though?
Cosine.
So cosine of theta
That's 3/5.
is 3/5.
Oh, you just flipped
You just flip it. Secant and cosine are reciprocals, so their values are just reciprocals. Okay. If we are now, remember, we're trying to find cosine and sine. We got them out of order. Not a big deal. Let's go back to this identity. Tangent of theta equal to sine of theta over cosine theta. Because right now, I have information about tangent. I have information about cosine. I need information about sine. So I use an identity that has all 3 pieces. What did it give us for tangent?
4/3.
4/3. What did it give us for cosine, or what did we get for cosine? 3/5. Oh my gosh, I messed up. Y'all didn't even stop me.
What do you mean?
What quadrant are we in?
Oh, we're in the 3rd.
So what is the only trig function that should be positive? So what should I do for my answer right here?
It's negative.
It's negative. When we took that square root, we should have used the negative version. My bad. I totally meant to do that on purpose.
It's fine, miss.
See if anybody caught my mistake.
Nobody did because we're too focused on the question.
That's right. You're listening so hard. Okay, so now I have cosine being negative. If I want to solve for sine, bless you, sine of theta,
Yeah.
how do I get rid of that denominator of negative 3/5?
You multiply it.
I multiply it on both sides. So I have negative 3/5 multiplied by 4/3. That's going to be equal to sine of theta.
Okay.
The 3's are going to cancel each other out. What is the sine of theta?
20.
What?
Wait, no.
What are you talking about?
Wait, what?
I got lost. Negative 4/5. All right, I know I just got lost a little bit. I'm assuming we all got a little lost. Can I answer any questions before we move on? Yes. Okay, that was actually a really, really great question. Did y'all hear it? She said, once we found cosine, it's like we found the x value and the r value, and then we already have the y value from tangent. So could we have just said negative 4/5? Oh, wait, wrong color.
Really, miss?
Yeah, we 1,000% could have.
So you're telling me I did all this extra work?
Yeah.
And we had the x, y, and r.
You actually could have done the problem exactly like we did in example 5, where you list out x, y, and r, because you're still given one of the trig ratios, meaning you're given 2 of the 3 pieces of a Pythagorean theorem. A squared plus b squared equals c squared. This is just a new tool in a toolkit that you can use.
Well, you're never gonna.
Mathematician's choice after this. These identities will come back for us later on in this course when we do simplifying identities. I believe that's chapter 5. We'll get there. But yeah, mathematician's choice. If you see it the other way, like example 5, totally do it like that. Or if you do half of it with this identities and then go back to the other half, absolutely, you could have. Great question. Any other questions?